Hello everyone, welcome back to another GIS mathematics lecture video. And in this lecture video I want to continue our discussion on sort of the fundamental principle that guides the basics of map projection. And so we're going to go through some additional sort of setting up different triangles and different arcs and figuring out how they all relate to each other. So what I've done is I've actually simplified our diagram from up here, right, our sphere with these 3 points on it. I've sort of removed the sphere and set up this three-dimensional axes. And I've put our points on here. So this point here, P, is again, this is the point on the north-south axis where our latitude is for points B and point C. So we have, you can imagine we would have a triangle that looks something like that. And then we have B, C, and A, and then we have these lines here. I'm going to actually make them solid here. Right, we have these lines, or arcs, I should say, because these would be arcs because they're on the surface of the Earth. We have these arcs that connect them to form a spherical triangle. Okay? And so what I want to do is I want to figure out, well, what lengths correspond to A, B, and what lengths correspond to BC. Right, so BC, oops. We want to find BC, and we want to find AB. Because if we can do that, right, then we know how to set up our triangle to be able to generate a shape on a flat surface. So let's go ahead and start off by finding AB. Right, so AB, I'm going to color this red. Let's find this length right here first, AB. Well, let's go ahead and draw ourselves out. Since A and B are on the same line of longitude, we can ignore the effects of longitude for now. And we can just look at a two-dimensional graph where we have our northing going in this way, and then this would be where the equator hits the Earth's surface. We'll call that point E. We'll call this point N. This is the center of our Earth, which we called O. And then I'm sort of recreating that diagram from the previous video, where we have our 2 points. So the first point here would be A. And we have our second point up here, which would be B. And all right, to sort of recap, the thing we're looking for is the length of this arc here. Let me try to make that a little bit cleaner. And we're looking for the length of this arc that connects points A and B. Well, we know a couple of things, right? First of all, right, we know the angle. Right, we know the angle here that the point makes relative to the equator. Right, this is our latitude. This is our latitude of A. Right. We know the angle that point B here. Let me make it a little bit. Right, we know our point B here because this B, right, this is our latitude, right, of B, which these would have both been given in, latitude and longitude, right? So we know that this is B, and we know that this is A. So hopefully it's relatively easy to see here that this angle between A and B is going to be theta B. Actually, let me do that in white over here. Right, the angle made by BOA, right, this is the angle that would subtend to this arc here, right, that's going to simply be theta B minus theta A. Right, and we have a special name for that. We're going to call that delta theta. Okay, delta theta. Well, we also know, right, we also know that the length of both of these is r. Right, the length of both of these lines is r. Right? That's the radius of our sphere, or in this case, right, that's the radius of our reference globe. Okay. So we know that r is the radius of our reference globe. But this is the radius of our reference globe. So hopefully you recognize now we have an angle, we have a radius. We can apply that arc length formula that we learned way back in the first section on trigonometry, right, where the length of an arc is just equal to the radius of the circle times the angle in radians of the arc, of the angle that subtends that arc. So this right here, this is simply going to be r delta theta. So we know AB is going to be equal to r delta theta, where r, again, is the radius of our reference globe, and delta theta is the difference between A and B in radians. Okay? So what about BC? BC is a little bit trickier. So for BC, we actually need to consider two different triangles. I'm going to scroll down just a little bit. We have to consider two different triangles. Right, the first one is going to be the triangle that we're actually interested in. And again, I'm sort of recreating these diagrams here, where we have C over here, and we have B over here. Okay. And so what we're looking for in this particular angle, right, so now we found AB. So now we're going to go and take a look and try and see if we can figure out what BC is. We're looking for BC, which is this arc right here, right, BC. Okay, so this is what we're looking for. And I should be clear here, right, that this point right here, this is point P. Right? And so just to clarify here, right, P is the point parallel to the equator. My handwriting's getting really bad. Hold on one second. Parallel to the equator at latitude, right, latitude B or latitude C, because they share the same latitude. Okay. So what we have to think here, right, we're going to eventually apply the same formula that we applied here, right? But now we have a little bit of a different issue, because this length here is not the radius of the Earth, right? Because if we scroll back up here, right, granted I may not have done the best job in the world here, but this length right here is not going to be the same length as this length. Right? So it's not going to be the same length as the radius of our circle. It's going to be a different length. Okay, right? So this is not going to be r. It's going to be something else, right? It's going to be PB, right? The distance from P to B. So we have to figure out what that distance is. And to do that, we're going to actually look at another triangle that's sort of hidden away in here. Okay? And that's the triangle formed by PCA. Okay? Or the arc formed by P. So let's look at another triangle. So you have point P here, right? We have point O here. So this is P, this is O. Okay, so this is that north, a little straighter. Right, this is that north-south axis that we have. This is our east-west axis that we have. This is E. Right, so we have our point A here. More importantly, we have our point C here. Okay. And so what I want to do, right, so we got this distance right here. Right, this distance is PC. Right? This is the distance from the point that is parallel to the equator at the latitude. Right? And then you can imagine drawing a triangle here. Right? This distance right here from O to C, right? From OC, right? This is the radius of our Earth. Right? This is R. This is R. This is PC. Okay? And this is what we want to know. Right? This is one step. Right? This is one step. If we get this, which means we can figure out this. I know this is a little bit complicated, so I'm going to take a step back. We know that this is going to be equal to the angle that subtends it, which is the difference in latitudes, times this length here. And we know that we don't know this length, but we can figure it out. We're going to figure it out by looking at the triangle created from the length that we want, the radius of the Earth, and the angle, and this angle here. Well, what is this angle here? We know this is 90 degrees. I should have specified that. We know this is 90 degrees based on the definitions that we've set up. Well, what is this angle here? That's a good question. Well, what do we know? We know that this angle here, let me do that in a different color. Right, we know that this angle here, and we know that this angle here is our theta C. A little bit bigger. This is our theta C. Right, this is the latitude of C. Okay, we know that. That's given to us again, right? We have all of these things in latitude and longitude. This is theta C. So we know this is theta C, which means that this whole angle right here, right? Let me do yellow. Right? We know that this angle, just a little bit from that. We know that this angle right here, right? That's going to be 90 degrees, right? Because this would be, by definition, a right angle, which means we know that this little piece right here would be 90 minus theta C, right? Because again, these two angles would have to add up to 90. But if you remember the rule of acute angles in a right triangle, right, that these two angles have to sum up to 90, which means that this angle right here is going to be the same as theta C. I know that was kind of a roundabout way of saying it, but I just want you to kind of understand where we come from when we say that this angle right here is also going to be our latitude of C. This is also going to be our latitude of point C, right? Okay, so now that we have that in place, let's go back and think about what PC would be, right? This gets to that idea of solving for an unknown side that we did previously. Okay, so let's think. We want PC, so I'm going to rename PC to be X. So if we want to know X, and we have an angle that is adjacent to it, and we have a hypotenuse, right? Because R is the hypotenuse of the triangle, right? Adjacent and hypotenuse, right? We can go back to that SOHCAHTOA, right? Cosine is adjacent over hypotenuse. And X in this case is adjacent. So what we can say here is that we can say that the cosine of theta sub C is going to be equal to, right, adjacent, which in this case is our X, over, right, our hypotenuse, which in this case is R. Right, rearranging this equation, right, because we can rearrange this equation, we've done this before, right, the length that we're looking for is going to be equal to cosine of theta C times R. Okay, so now we can go back here, right, and we can label the length of this thing to be cosine theta c r. Okay? And then we know that this angle is going to be delta lambda, right? We already discussed that in the previous video where we set up some of these triangles. Right? And so we know that the length of the arc, again, going back to the same thing we just did, right? The length of the arc is going to be equal to the length of the radius of the circle, which in this case is cosine latitude of r, or sorry, cosine latitude of c times r, times delta theta. So we know that this is going to be equal to the cosine of the latitude of c, or the latitude of b since they share a latitude, times r. Right, that's the length of this radius, of the radius of this circle here, times the change in theta, or delta theta, which is the difference here between b and c. Okay. So now we have the length of two sides of the triangle. Right, one is going to be equal to r delta lambda, or sorry, r delta theta, which is going to be the difference between b, a, and c. That's one side of the triangle. And the other side is going to be cosine theta c times the difference in latitude, the difference in longitude between b and c. I know this was a lot. I really encourage you to pause the video, go back, rewatch the different parts, make sure you understand where each thing is coming from, because these two equations are going to be fundamental for understanding how we move forward with projections that are trying to preserve the different types of distortions. So hopefully that makes sense. And as always, please reach out. Thank you.